Hello, welcome back. Today we're going to continue our discussion on the concavity test. From yesterday, we talked about how we can determine from a graph where the concavity changes. And we said we're going to look for the second derivative this time, where the second derivative is 0 or d and e. And we call these possible points of inflection. This is where the concavity changes. And again, where we go from concave. So if I have a function looking like this, at some point we're going from concave down to concave up. And the inside here is a POI. Now yesterday we talked about them graphically. Today we're going to talk about them algebraically. So, and then we said we would draw a sign chart just like the first derivative test and determine what the concavity was. And the example that we had given, so let's take a look at an example, So we're given the function cosine of 2x. We want to find out if the function concave up or down at pi over 6. Well, anytime we talk about concavity, we need our second derivative. And I can do that really quickly here. If we take our first derivative, that's going to give us negative sine of 2x times 2. Don't forget your chain rule. Taking the second derivative, we're going to get negative cosine 2x. Now, I'm already multiplying by 2, but when I multiply by 2 again, I'm going to get 4, our chain rule. So my second derivative would be negative 4 cosine of 2x. And all I have to do is just plug my pi over 6 in. We're going to get negative 4 cosine. This becomes just pi over 3. And the cosine of pi over 3 is just positive 1/2, so this becomes a negative 2, because I take that 1/2 multiplied by negative 4, get negative 2. Notice this is less than 0. So we can actually answer the question. This is going to be concave down, so we will say f of pi over 6 is concave down because the second derivative there is less than 0. There's our answer. Very easy to do. Alright, so let's talk about how we can solve these algebraically. So we're given a cubic function. We want to use sign charts to find the points of inflection and then discuss the concavity, concave up or concave down. So if we look at a question like number 1, we're going to need the second derivative. So if I take my first derivative, we would just get x squared minus 1. Our second derivative is just going to give us 2x. There we go, second derivative. We now want to find our possible points of inflection. Our rule here, we want to find out where is the second derivative 0 and where does the second derivative just not exist. Now notice we're not dividing by anything, so we don't have to worry about the d and e here. But we do have a spot where it's going to equal 0, and of course that's just going to be 0. So we have one possible point of inflection. Notice this is just like our first derivative test. And next I'm going to do a sign chart. Well, on my sign chart, I'm going to take the second derivative, and I want to see how that makes my function look. There's no domain restrictions. My one critical number is 0. Possible point of inflection is 0. And if I pick a negative number and a positive number, just going to pick a negative and a positive. I'm plugging it into my second derivative, which is 2x. Well, if I plug a negative 1 in, that's negative. That's telling me we're concave down here. If we plug in 1, we get a positive. We're going to get something concave up. So I can answer the question, do we have a POI? Yes, f has a POI at x equals 0, and there's two reasons for it. One, because the second derivative is 0 or d and e, and 2, the second derivative changes signs. You definitely need that second one. Now they also ask us to discuss the concavity. So I can say this, f is concave up on the domain 0 to infinity, and that is because the second derivative is positive. And I can say f is concave down on the domain negative infinity to 0 because the second derivative is less than 0. Very easy to do these. All right, so let's do a hard one. Number 2 here. Number 2. Here we have a curve, one of the witches of Agnesi, and they call it that because they make this kind of like a little bell curve right here. It looks kind of like a little, maybe like a witch's hat. So we want to take the first and second derivative here. So I'm going to do this real quickly. Now I'm going to cheat a little bit for the first derivative. I'm just going to bring that x squared plus 3 to the top. It sounds kind of weird, but I'm going to actually use a chain rule for this one for the first derivative. And if we do that, we will get the first derivative equaling negative 6 x squared plus 3 to the negative 2 times 2x. Simplifying it, I don't like this, so I'm going to rewrite this. And this becomes negative 12x over x squared plus 3 squared. Now I'm going to use my quotient rule. I don't want to do product rule. Product rule is too nasty for this one. So I'm going to use my quotient rule, which says take the low, x squared plus 3 times the derivative of the top minus the top becomes plus 12x times the derivative of the bottom, which is 2 times x squared plus 3 times 2x. Whew. All over the bottom squared. Whoop, I forgot my square here, didn't I? There we go. That should be a square there. All over the bottom squared. X squared plus 3 to the 4th. Now this is pretty ugly, but you're going to notice things are going to clean up really nicely. For example, I can factor out and divide an x squared plus 3. So that goes away. That's completely gone, and that becomes a 3 right there. And so my second derivative will become, if I distribute here, I'm going to get negative 12x squared minus 36 plus over here 2 times 2 is 4 times 12 is 48x all over x squared plus 3 cubed. Whew, nasty. Which I can still kind of clean up a little bit here. All right. Negative 12 plus 48 is 36. Whoop, that should have been an x squared there. My pen's not working too well. 36x squared minus 36 over this x squared plus 3 cubed. And now we can find our possible points of inflection. So let's go and do that. PPOIs. Where does the second derivative equal 0? Well, that's the top. 36x squared minus 36 equals 0. You can solve this. That's just plus or minus 1 right there. Where does the second derivative not exist? That's the bottom. I don't worry about the cube. It's just going to go away. I get x cubed plus 3 equals 0. Whoop, not x cubed. X squared. So we get x squared equals negative 3. Try solving it. Not going to happen. So we only have the 2 possible points of inflection. Whew, fun times. So we do our sign chart. Negative 1 and 1. The second derivative, which again is this 36x squared minus 36 over x squared plus 3 cubed. Now I am in luck, and if I'm good at math, I know the bottom's never going to be negative. Positive, positive, positive. So now I just pick a number, like negative 2. If I pick a negative 2, that becomes 4. 4 times 36 is bigger than negative 36, so this is going to be positive, so we know we're going to be concave up. Plug in something like x equals 0, and I get a negative on top, so we get concave down. Plug in something big, like 2 again, like if I plug in 2 here, again, 4 times 36 minus 36 is going to be positive. So we got concave up. So we we got POIs. So we have 2 POIs at x equals plus or minus 1, because 2 reasons. The second derivative is 0 or D and E, and 2, the second derivative changes signs. That's what I'm looking for there. Concavity, let's discuss the concavity. F is concave up on the following domains: negative infinity to negative 1, or 1 to infinity, because the second derivative is positive. F is concave down on the domain negative 1 to 1, and that is because the second derivative is less than 0. Ah, how much fun that is. All right, go to the next video. We'll take a look at a couple more. I'll see you then.